Okay, hello everybody, and today we're going to talk about the Weierstrass function. So let's talk first a little bit about some motivation for why you should, why Weierstrass came up with this function. So at some point in the history of mathematics, they developed the notion of a continuous function. And so we could write down some examples. For example, the function x squared. We have the function cosine of x. Here we have the function absolute value of x. Okay. And then at some point they developed the notion of differentiating a function. And so you could differentiate this function. You get 2x. This function is a negative sine of x. And this function is the sine of x. It's not the sine, but the sine of x. It's if your input number is positive, it outputs 1, and if it's negative, it outputs negative 1. But there is actually a little bit of a problem, because you can't really differentiate this function at the origin. There it makes a sharp angle. And so you call a function differentiable at a point if you can find the derivative in that point. So differentiable. That's what we're going to talk about. Being differentiable, and it looked like they've seen all of these examples, and well, there was a little point up here which wasn't differentiable, and well, you can maybe think of maybe an even further example where there's loads of points where it's not differentiable. But at least you'll see that that most of the points the function is differentiable. So you might think if you have a continuous function, then you at least have one point where it is differentiable. 1 point differentiable. And that might be a reasonable guess, but it turns out it's totally wrong. There are loads of functions which are continuous, but there's not a single point where the function is differentiable. Those functions are actually called fractals, and they're kind of nice. But the first function which came around, which they proved to be continuous, but never for any point on the function be differentiable, and that was the Weierstrass function. Actually, the Weierstrass functions, because it's an infinite family of functions. So I'm gonna draw a picture of the function the best I can, because it's kind of a weird function, but it goes a little bit like this. So like this, and then like this, and yeah, something like this. It goes really up and down, and the point is that if you zoom in on such an area, it looks exactly the same as the bigger picture. That's and it's the fractals sometimes do have the property. The actual definition of a fractal is having the same sort of complexity on each level, but we won't dive into that much right now. But there's nice pictures to look up at on the internet. But remember, at the time Weierstrass proposed this function, they didn't have any computer or such a thing to make an actual picture of this function. So they know they could prove this function is continuous and it's never differentiable, but they actually had no idea how this function would actually look like. So it's kind of interesting, of course. So I'm now going to tell you what the function is. The function is defined like this. We have the sum going from n equals 0 to infinity of a to the n, and then we have a cosine of b to the n times pi times x. And here a and b are parameters, and we want a to be between 0 and 1. We want b to be an odd integer, and furthermore we want a times b to be bigger than 1 plus 3/2 of pi. Okay, so the first odd integer b for which there exists such an a will be 7, but that doesn't really matter. Okay, so we're going to show now that this function is continuous. We're not going to show it's differentiable. To give a complete proof that it would be kind of long and tedious. You can find it online. There are kind of some neat proofs if you want to look into it. So let's first prove that this function is continuous everywhere. And for this we're going to use the Weierstrass m-test. The Weierstrass m-test. And what does the Weierstrass m-test say? It says if we can bound the absolute value of all of the inputs from our sum by another function which does converge, then we know the first function does absolutely and uniformly converge. So let's write that down. We want the absolute value of our of the things we're summing over. Cosine of b to the n pi times x. Now, and well, of course, this is going to be always less than or equal to a to the n. And because this cosine, no matter what you put into it, cosine will be at most 1, at least -1. And we're putting real numbers into it right now, so over the complex numbers, the cosine can get way bigger, but it's something else. So we see this thing holds, and of course the sum from n equals 0 to infinity of a to the n does converge, because a is in between 0 and 1. So this implies that our function f of x does converge, but not only converge, it converges absolutely and uniformly. And we only need this second condition, because now we can say that the partial sums of our function, if you take some number capital N, then we can define a function with respect to capital N of x. This will be equal to the sum from n equals 0 up to capital N of a sub n cosine of b to the n times pi times x. Then this is just a finite sum of cosines with some constants. So of course that will be continuous, it will be uniformly continuous. So therefore, by the series converging uniformly and the partial series being uniformly continuous, we can conclude that our function itself is uniformly continuous. So and thus continuous. So that's our big conclusion. Okay. So that's nice. Now we're gonna show a little bit of an intuition for why this function should be non-differentiable everywhere. So again, we're going to take the partial sums. So f of n of capital with respect to capital N was the sum n equals 0 to capital N of a sub n, the cosine of b to the n by x. And now, of course, this is a function which is differentiable everywhere, because it's just a finite sum of cosines. So we can take the derivative of this function. So f prime of this nx function will be equal to 0 to the n. Now first we have a to the n, and then we have this cosine b to the n by x. So remember, when using the chain rule, or the chain rule as Dr. Payam likes to call it, we get, for differentiating the cosine, we get a negative sign. Sine of b to the n by x, and then we have to multiply by the derivative of the inside. So that's going to be b to the n times pi. And then we see we get a bunch of constants in the front. So we won't worry about those. 0 capital N, and here ab to the power of n sine of b to the n by x. And of course we have the condition ab is bigger than 1 plus 3/2 pi, which is of course greater than 1. So this sine function will bounce a little bit. This will just continues make some sign change, but this thing will go to infinity. So you see, it would be kind of hard to find a exact value for b such that this thing would actually converge, because that would mean that our function itself would be differentiable at this point. And actually it's just impossible. But this is, I think, a great intuition for why that should be the case. But again, if you really want to dive into it and see the proof, you can find it online. So that's all about this weird Weierstrass function, continuous function, everywhere but nowhere differentiable. Okay, and I see you guys another time.